we can look at another problem which deals with these. So, it says a frictionless vertical piston cylinder assembly fitted with an electrical resistor contains air. The mass and the face area of the piston are given as 50 kg and 0.1 meter square. So, let us write that down. The piston has a mass of 50 kg and an area of 0.1 meter square. So, we have a vertical piston cylinder assembly by which we assume that the piston is on top of the cylinder. So, I am guessing at some point we are going to look at this substance below. We will change it if that is not the case. This should have been a straight line. I am sure you understand that. The atmospheric pressure is 100 kilopascals. This piston cylinder assembly also has an electrical resistor. Okay, so we are going to mark the electrical resistor and we will also mark atmospheric pressure as 100 kilopascals. So, let us do that. So, the pressure here is 100 kilopascals. So, there is some electrical resistor here. So, let us say there is an electrical resistor of this kind. So, what we are going to consider as our system is essentially all the air, but not the electrical resistor coils. So, our system consists of this portion and this portion, but not the electrical resistor itself. So, that is what we are going to consider as a system for the time being. Electrical current is passed through the resistor, causing an increase of 0.05 meter cube in the volume of air. So, what we see is that the volume increases and the increase in volume or the change in volume is 0.05 meter cube. So, what we see is delta V is 0.05 meter cube. So, as we heat this, the pressure here would tend to increase because we are heating the air. Because of it, it tries to push away the piston and the volume increases. So, we have this. The mass of air is 0.4 kg, which is a constant, because as long as the piston is here and we are assuming that the piston is leak proof and frictionless, nothing can go out. So, we have that also. Because of heating, its specific energy increases by 43.3 kilojoule per kg. So, the specific energy is delta E, which increases by this. Assume the assembly including the piston is insulated and acceleration due to gravity is 9.8 meters per second square. So, what we are going to do is insulate all of this so that no heat can go out through the walls. We will also consider the piston to be insulated, no heat can go out through that. So, any heat transfer through this electrical coil, all of that energy must be remaining inside this. It cannot go out as heat. So, that is something which we see, and we are given acceleration due to gravity is 9.8 meters per second square. We are asked to find out the heat transfer from the resistor to the system for a system consisting of only the air or the air and the piston. So, let us do A first. So, in A, our system consists of only the air. In B, our system consists of the air and the piston. So, that is what we are going to try to do, find out Q. So, what you want to find out is Q. So, the first case, our system is as shown, it is only the air, that is our system. So, we have the mass of air, we have the change in volume, we have the pressure outside, we have the mass of the piston, and we have the area of the piston. So, what we can do is try to think of what process is happening over here. So, we are heating the air inside, the air is trying to expand and move. So, what is resisting the movement of the air? So, one of the things which is resisting the movement of the air is the weight of the piston. So, the piston has a mass of this. So, correspondingly the weight of the piston or the force downwards due to the piston would be this. So that is resisting, and the other thing which is resisting is the atmospheric pressure on top. So if you were to look at the movement of this piston, so the downward forces are mp into g and p atmosphere, and what is trying to push up this piston is the pressure of the air inside. This does not change because the mass of the piston is fixed, acceleration gravity does not change, atmospheric pressure is also fixed, 100 pascal, it does not change. Therefore, if this is happening in a quasi-static process, if it is happening close to equilibrium, initially also this piston was at rest, later on it is moving very, very slowly. So then the pressure of the air at all points of time must be equal to this. So if that is the case, then this must be essentially a constant pressure process. So by looking at all of this information, we can reason that this is a constant pressure process. So now we have some idea of the process. Our process is a constant pressure isobaric process, which we can write as V equal to constant. We can also find out what is the pressure, because we know the P atmosphere is 100 kilopascal. Of course, this is not a correct equation because this is force and this is pressure. So what we need to do is divide the force by the area, and we would get pressure. So we have the mass of the piston, which is 50 kg, into acceleration due to gravity is 9.8 meter per second square. So that is kg meter per second square, and we are going to divide it by area, which is 0.1 meter square. So we had kg meter per second square, so we get kg per meter second square, which is essentially a pascal. So this would be the atmospheric, or sorry, this would be the air pressure. We can find out this. Which is, so we find out that the air pressure is equal to 104.9 kilopascal. So we have this. We want to find out Q. We don't know a way of finding out Q directly because we do not know the temperature. So what we are going to do is try to use the first law. So again, the first law tells us that dE is del Q minus del W, or in the integrated form, delta E is Q minus W. I have some way of finding W because I know the process, I know the pressure. So what I am going to do is find out W. Over here, del E is given already. What we will also see over here is that it is air. When you change the volume of the air, the potential energy of the air does not change significantly. The kinetic energy does not change at all because the air is at rest. So I can also, in this particular case, write this when I have only air as a system, and I know that value. So delta U is given as 43.3. So delta capital U would be m into delta small u. So the mass of the air is 0.4 kg, into the change in energy is 43.3. This would have units of kilojoules. I can find out the work. This is expansion against a constant pressure. It is expansion work for a simple compressible substance, which is generally given as PdV integral. And since the pressure is constant in this particular case, which just becomes integral of dV, which is essentially P into V2 minus V1. I know the change in volume, it is already given. So this is essentially 104.9 into 0.05. This is in kilopascals, this is in meter cube. I will get units of kilopascal meter cube, which is essentially kilojoules. And knowing these two, I can find out Q. So Q is essentially delta E plus W, and I'll get some value in kilojoules. So let me just find out these values quickly. So this is 17.3 This is 5.24. This is 22.5. So, the first part of this problem is done in this fashion. I can get the value. The second part of the problem tells me to do the same thing when I consider the system as both the piston as well as the air. So, I still have this heater here. So, my system is still the air on this side of the heater, and the other side of the heater does not include the heater, but now includes the piston as well. What I am interested in finding out is the heat transferred. What we can see is, we can do this problem and find out its value numerically, but even without doing this, what we can see is this. This is now part of the system, but this is insulated. So, there cannot be any heat transfer through this. There is also no heat transfer to the sides because the sides are also insulated. So, the heat transfer in this case, including this piston as part of the system, must be the same as in the previous case. So, even without doing this problem, I can tell you that the heat transferred in the second case is 22.56 kilojoules, because I have calculated it earlier. This is insulated, there is no heat transfer to the top. Therefore, in both the cases, the heat transferred from the, however I analyze it, the heat transferred should be the same. So, I know the value of that. But if I was to do this problem, what would happen now is the other things would be slightly different, because if I was to consider the piston as part of the system, then when the piston is moving up, the air is not doing work against the piston because the piston is now part of the system. So, what happens is, if this is now part of the system, in terms of work, when I look at it, I am only doing work against whatever pressure is here. So, the work now is only work done against the atmospheric pressure. So, that would change. And if I am looking at internal energy change, I know the change in energy of the air, which is given. But now I would also have a change in the potential energy of the piston. So, that is something which I would have to take into account, which is essentially m into g into whatever the height by which it is raised. So, the piston is moving upwards. So, the final height would be higher. So, the internal energy change for this piston would be positive. Sorry, the potential energy change. So, I would have this, if I am now looking at delta E for this system, including the piston and the air, I have the change in energy of the air, which is delta U, plus I would have change in energy of the piston, which will be given as this. So, the energy change is now different because I have this as part of the system. The work done is different because now I do not, in this case, I was doing work against the piston weight as well as the air. In this case, piston is part of it. So, any change due to the piston is considered as energy change, and I am only doing work against the air. So, those two change, but the heat transfer itself does not change. So, we could calculate it. So, this is easy to calculate. Delta V is given as 0.05, and we have the air pressure as 100 kilopascals. So, that is 0.05 into 100, which is essentially 5 kilojoules. Over here, what we have is m into delta U is the change in internal energy of the air, plus mg into delta H for the piston would be the change in energy of the piston. So, if I was to look at delta E for this system, it would be 43.3 into the mass of air, which is 0.4, plus mass of piston, which is 50 kg, into acceleration due to gravity, which is 9.8, into the height moved by the piston, which I do not yet know. So, I can find out the height moved by the piston because I know the area of this piston, I know the initial volume, I know the final volume. So, I can find out what is the height by which this piston moves. So, putting those together, I should be able to find out this value. So, let me do it anyway. So, the initial volume was the change in volume is 0.05 meter cube. So, this 0.05 meter cube is a cylindrical volume, which must be pi d square by 4 into height, essentially the area of the piston into height. This is given to me as 0.1 meter square. So, I can find out height. So, the change in potential energy of this piston is essentially this value, 50 kg into 9.8 . Which is 245 joule, if I have done this calculation correct. And I had here the remaining portion 43.3 into, I had this 17.32 kilojoule is the change in energy of the air, is this. The work now is, we had calculated that already, that is 5 kilojoule. So, heat transfer is delta E plus work, which is 5 plus 17 plus 0.245 kilojoules. So, this is about 22.5 kilojoule is the answer I get if I do this exercise. We see earlier that we got 22.56. I did not add the second digits in this case, you would get the same. So, I can do this exercise in this fashion. I see that because of the way in which we define the system, the values of the work and the heat and internal energy in general can change. In this particular case, because I use a different system in the two cases, the work has changed and the energy change has changed, but the heat transfer is still the same. So, in this particular problem, the heat transfer does not change. So, I needn't have done this exercise, but it is reassuring to see that even if I do it, I get the same thing which I can deduce by logic initially without doing this problem.